Okay, let me slowly start welcoming everybody. Great to see some of you again. For those of you who are new, very happy you could join us. So this is now I think the fifth in the meantime of our monthly SPIA webinars, where we are trying to use this platform as a way of showing different ways that researchers have gone about or thought about providing empirical evidence of impact related to CGIAR innovations or CGIAR research activities more broadly. Today, we have another great example of a very innovative approach where I think there's innovations on many different fronts where lots of other people hopefully can learn from, both in terms of even making it possible to do an impact study so both in terms of the actual work around Masago in Mexico, that is circa hands-on, but then also the database that was put together, the approach that was taken to do that, and then the link to the impact assessment work and the innovations on the measures and the methods there. And so this is going to be this is exciting. It's also going to be a lot to talk about, and so let me not take too much time now that I see most people are there, and jump straight into introduction. So very happy to have with us Andrea Gardeazabal from CIMMYT, who will do the first part of the presentation, and then Joel Ferguson from UC Berkeley, who will take over next. If you have any, if during the presentation there are any clarification questions, feel free to use the chat, and we'll keep an eye on that. And then, other than clarification, we'll have a presentation. The two presentations more or less will take 60 minutes, and then we'll have an open Q&A where we'll open the mic and have a broader discussion. Take it away, Andrea. Thank you.
Thank you, Karen. So, good morning, afternoon, evening to everyone. Thanks for joining us in this session. I'm going to be sharing my screen. Can you please confirm if you see it in presentation mode? Yes, okay. So thank you again. I'm Andrea Gardeazabal. I work for CIMMYT in monitoring, evaluation, and learning. And for this session in particular, I'll be introducing Joel's presentation by walking you through the tools and processes we have in place, not only to monitor projects, but to make the best use of these data we generate within them. In this particular case, we have done, I'm going to be presenting how we did and how we collect a specific data set for the plots with sustainable practices that are monitored and advised by extension services in Mexico to analyze agricultural fires and the correlation with infant mortality, which is what Joel has designed. So I'm going to start talking and introducing you to the field innovation model that we have and the way we approach to the farmers in the field. So in addition to maize and wheat improvements, CIMMYT also does research related to farming, doing farming more sustainable by improving growing practices and by co-designing innovative and affordable technologies in the field. This is done mainly through this participatory research approach organized in agroecological distinct hubs. So each hub has basically a physical infrastructure, including research platforms, modules, and validation plots. And what we do here is we generate knowledge co-creation, and we basically test innovative practices within the research platforms with basic research coming in. In each region, we validate this with the farmers in validation plots. And once we have a portfolio of technologies, sustainable technologies that we can actually say it's, let's say, fits the needs of the field and fits the needs of the farmers, then we go to extension areas and impact areas. So we have these four types of plots and different types of areas where we actually foster co-creation and knowledge exchange. On top of this infrastructure, what we build is basically networks. So we have hub managers in each region, in each agroecological region, and we connect different local actors around the sustainable practices. So we have very close connection in, relationship management with input suppliers, local governments, buyers, uptakers, extension services, NARS, among many others. With these basic model, what we normally do is that we monitor processes in the field. We monitor this research process, but we also monitor the adaptation process of the portfolio of practices within the particular context of farmers. And we also have very close connection and partnerships with extension services in the field, which help us to monitor these processes, to accompany the farmers in the field with this process. So this infrastructure, as I said, is just to build this network of stakeholders, and in order to promote the diffusion of knowledge from research platforms to farmers, as well as to facilitate the incorporation of feedback from farmers into studies performed at the research platforms, we connect all these dots. CIMMYT forms partnerships with many private and public extension providers, in particular for these study. What we've done is we collect information with local extension services providers, and what we normally do is we hire, or we make specific relationships with them to make use of the data collaboratively, let's say. So all the extension services that we work with in the field with provide methodological and technical backstopping, and record data at least twice a season per plot. So we have this system, which is the eAgrology, is an agricultural data platform, and all these extension services that I'm mentioning that we work with collect data specifically from each plot at least twice per cycle. And they help us to monitor these agricultural and sustainable practices in the field. Masagro, a 10-year project funded by the Mexican government, supported the beginning of the field database. So they supported us with the design of these database, with the design of these data collection system that now we can call an agricultural data platform, because we have evolved from what was at the beginning just a field data book into an agricultural data platform. And we have included at least 500 variables approximately per plot, per production cycle, where we collect very detailed information about what's going on in the field. Plots can adopt multiple technologies, where conservation agriculture is the most widely adopted technology, I would say, because we have the longest experience in research experience in the field with conservation agriculture. So we have the most widely adopted technology as the conservation agriculture. And we have technicians who learn of other plots on which the technologies they promote are being applied, record data from the plot as an impact area once, and then include some of the basic data on farmer characteristics, technologies, and again, the plots centered. So what we normally do is we collect data very detailed data from research platforms. Then we collect detailed data from the validation plots, which is basically data sets that record the comparison side by side. So in each side of the plot, we record the same data where we have the traditional or the conventional technology versus the innovative technology, or the innovative portfolio of technologies, of sustainable technologies. We collect both. And then we have in the extension areas and the impact areas, we have just one set of data, different in terms of detail for each of them. We basically collect, these are the main features of the system. We collect the user profile. So we are able to organize data per profile for farmers, for buyers, for extension agents, and for input providers. Specifically for these data set, we're going to talk about the farmers' profiles and the way we work with the extension agents. We collect plots and sites. We have polygon registration. So we're not only collecting the coordinates for one plot, but we collect the polygon as well. For this particular study, we use a data set with coordinates from the plots that I was mentioning here, these numbers of plots. So the modules, this is the distribution between modules, extension areas, and impact areas that we have in the system. Again, we collect plots. Then we have the agronomic field book, where we collect management practices, costs, income, post-harvest activities as well, and commercialization. We do also monitor extension services related to how the technicians do the field visits tracking, and we use that to monitor pest and disease tracking. We also have opportunity to gather data regarding farmers' organization, community planning, how they are related to groups registration and the work and collaborative production, and information services at the end that we have that I'm going to mention them because we have them as part of the agricultural data platform, but we're not specifically used for these study. Our dashboards with yield, cost benefit, and natural resources conservation, real-time pest and disease tracking, and site-specific recommendations. So this is basically the flow that summarizes the integration of processes that we have. We have a data collection system in the field that it's run, as I said, by the extension agents that collect the information of all the fields of the model that we have. We also integrate satellite imagery and related to soil and some of the information, and we also integrate that with weather. In this particular study, Joel has done a process for integration specifically with the data set of the plots, and he will talk about the specifics on the analytics that he did. In other processes that we have, we normally integrate and clean these data sets in order to generate the basic analysis for cost benefit, soil fertility, and agroclimate services for site-specific recommendations for the farmers. And we have an output here, which is a mobile application that it's called AgroTutor, that it's normally the channel through which we go directly to the farmers with the recommendations that we have from these data sets and the integration process of the data sets as well. This is a very general map on how the Mexico map we can see the other view of the Mexico map with the data collection that we have, combining modules, extension areas, impact areas, and research platforms. We also collect data from machinery points. That is another type of site that we have, which are not necessarily plots, but just sites where machinery can be hired or gathered, and some of the type of sites or infrastructure that we have in the field to build the whole hub model that I was mentioning before. So basically what we have in the e-agrology system is a monitoring system for the e-agrology model, for the model of the hub. So the hub is the basic way through which we intervene in the field, and we have this monitoring system to gather all the data. Again, I'd like to insist that we use the extension services at the local level. We partner with them in a very close way. We train them as a way that they can also train some other groups to be able to collect data in the system. So the main incentive to collect the data for the system would be the use of the data. So let me talk a bit about it and what we have done, because that's the way we see this strategy. I mean, that's the way we've learned that the strategy actually works, because if we don't offer something really interesting to the extension services, then it's not likely for them to generate this whole data set that we have at the moment. So normally what we offer is this type of analysis to them. We've done cluster analysis where we actually compare not plots side by side, but we compare different types of different criteria of each farmer, for example, weather or management practices, or combining weather management practices and plots and their crops. So we do this different types of cluster analysis, not only territorial clustering, but different types of clusters. And with that clustering exercise, we do scenarios for decision making. So the one that I'm showing here at the bottom is basically a distribution of yield in different groups of different clusters that we have. And for each of them, for each of the clusters, we say how would be the yield with a particular variety in that particular context. So we're not suggesting varieties based on territory necessarily, but we're suggesting varieties based on the cluster analyses, combining weather with management practices. Other thing, and this is very interesting for the technicians and for the extension agents, when it comes for them to make recommendations to the farmers. We also do what we call benchmarking, which is basically comparing each of these dots is one of the plots that we have registered in the system, and we here compare profit with yield. And you can see this is a particular region, this is a territorial comparison, and here you can actually see who were the farmers or the plots that had the best progress in this particular region. So best yield with best profit, and we go directly to these logbooks in the system, and here in the bottom you can see the timeline of activities, very detailed activities, very detailed information in terms of what these farmers did in that particular cycle. So we go back to these region farmers with these analysis for the extension agents to have these analyses to be able to recommend based on the benchmarking that we do, to recommend to the other farmers to be able to go up here. But it's not only about results related to yield and management only. So we also do network analysis where we see which farmers are best connected to others, which farmers are best connected to, let's say, have access to finance or have access to inputs. So we are not only recommending something that is not necessarily feasible for each of them. So maybe this one is a woman that has a very little plot, and she does not have access to finance, and that's why she got these results, right? So we also do network analysis, trying to understand who is who in this network and how we can actually help them to be as connected as necessary to have those results. And finally, these are some of the examples that we have as output channels. So I was mentioning AgroTutoras, our main channel to connect to the farmers. We generate the recommendations that we generate are all channeled through here, and this is an app that is geolocating data. So you just go log in, you say where you are, where your plot is, and the application will retrieve all the geolocated information and bring it to you. And also we have these type of tools, which is an optimal fertilization tool, recommendation tool for bigger plots. And for this is particular for monocropping in bigger areas in Mexico. This is more for smallholder farmers in the south of Mexico. So that's why we have built different strategies to communicate to them. And finally, we have online interactive dashboards for donors and for intermediaries in the value chain that actually also need access to these information and want to see aggregated data related to yield, to costs, production costs, even management practices, pests and disease, and so on. I'd like to finish my presentation by saying that we actually protect very carefully the data privacy of farmers. The data is from the farmers, and we go back to them with the main results that we have. We want them to use the data at the end. So we only share anonymized information with other parties, third parties. We're promoting and we foster the use of this data. So we're very pleased that Joel had this idea of doing these type of research, because this is what we actually want. We have this data set to be used, but we protect from the beginning the data privacy, and we don't share any personal information with any third party, at least unless we have specific consent from the farmers. So I'm going to stop there. Thank you very much for your attention. And Joel, please take the floor.
Thanks, Andrea. I'm going to share my screen. Let's see. Can you all see that?
Yeah, all set.
Okay, great. So I'm going to talk now about a project that was started in late 2019, basically to try and evaluate some impacts at scale of moss agro. And so basically the idea was that now you've seen that there's kind of this incredible data collection effort associated with moss agro, but you know, to do some sort of impact evaluation, we need data maybe for farmers who aren't engaged in, or you know, who aren't receiving extension services, or you know, from before the farmers started receiving extension services. So the idea was that we could bring in remote sensing to make some outcomes available for this type of analysis. So today, I'm going to talk a bit about some of the lessons that we've learned during the process of doing this this project. I'm going to mostly focus on some of the statistical methods related to space that have been used or I'm trying to incorporate now, and show you some of the still preliminary results. So before getting into anything about causal identification or anything like that, I want to focus on some sort of pre-analysis type decisions for studies maybe like this, where there's an intervention that has taken place and we want to now evaluate it kind of retrospectively. So maybe the first thing to do with a study like this is to define what we mean by treatment, which maybe sounds simple if it's a retrospective study and the intervention has already taken place, but understanding what exactly we mean by treatment is important for determining how we think about a lot of aspects of the study, like how we actually measure this variable, how we think about identification in a causal inference setting, and how we think about the generalization of results. I'm going to get into it more a bit later, but when we start thinking about where units are in space, we have to be even more careful with kind of how we think about some of these things. So I've mentioned the stable unit treatment value assumption, or SUTVA, or spillovers is maybe a more common way to call it, is something that we have to keep in mind when we think about what is treatment with these kinds of studies. And then measurement error is also kind of something that we always have to keep in mind, but maybe becomes especially important here. So for us, it's much easier to measure the provision of knowledge than say like diffusion, because as Andrea was saying, these data are collected by extension technicians, and so you know, necessarily extension technicians need to be around to collect the data. So kind of the treatments that we're focusing on are the introduction of moss agro extension and techniques and technologies, as well as kind of intensive measures related to the provision of extension. So once we have a treatment figured out, we have to choose what we want to look at as outcomes. And then basically, I think that anything that answers these three questions, what are we interested in, what do we think might be affected, and what is measurable, should be included as an outcome in a study. So kind of the first things that maybe we think what might be affected for moss agro, maybe yields and diffusion come to mind. I was also kind of particularly interested in looking at residue burning from the beginning, and as we kind of proceeded with this study, it turned out that it was pretty hard to reliably measure yields and diffusion in a way that was kind of really compatible with causal inference, but residue burning not only kind of seemed to work, it also looked quite interesting. And so we kept working on this outcome and kind of added some related outcomes like health, so infant mortality in particular, and then a moderator of the relationship between residue burning and infant mortality, which is air quality. But I won't focus on these results today. So really quickly, I kind of just wanted to say something about how we got to residue burning in the first place. It's not maybe the most obvious outcome to look at, but when I was kind of reading up on Mass Agro, I saw infographics kind of like this that kind of mentioned, burning in traditional agriculture and in conservation agriculture, avoiding that. And I guess as I looked into it more, I also started to realize that it was quite easy to detect fires from satellite imagery, and that crop residue burning is kind of widely practiced not only in Mexico but throughout the world, and generates a lot of air pollution. So I thought that it could potentially be a pretty interesting outcome, and it turns out to have, I think, been very interesting. So kind of the last pre-analysis decision I guess I want to talk about is choosing the unit of analysis. So when we're thinking about doing an analysis with units that are arranged in space, and we're thinking explicitly about space, maybe there's a tendency to think we want smaller units. This makes sense from a statistical power point of view, because all else equal, if we have more units, we should have more statistical power to discern effects. And then also, the smaller we break up the data, the more we're able to look at treatment effect heterogeneity that may have been covered up if we had done a more aggregated analysis. But there are a lot of reasons to maybe use bigger units. So one is that we actually have to be able to assign values of variables to units in a systematic way, and generally super disaggregated data aren't available for everything that we want to measure. So that will tend to push us towards using bigger units. Otherwise, we have to somehow interpolate data. Stable unit treatment value assumption issues, so spillovers, are a classic kind of issue for causal inference. And so ideally, we can make units large enough to capture spillovers, although that's not always possible. And I'll talk a bit later about how other ways that we can deal with spillover type issues. And then measurement error is kind of always a concern, but with some of the methods that I'll be talking about, it can be kind of especially pernicious. And so and when we start thinking about where units are in space, we get kind of this extra element of measurement error, which is we have to know where in space we are measuring variables. And so that is also something that if we want to be sure we can assign variables in space, well, we should try and make bigger units. So what we've settled on for this study is a 0.1 arc degree grid. This map shows the first year that a plot appears in the database that Andrea was telling you about. So in each grid cell, and kind of one of the things that you can see in this figure is that it shows some interesting heterogeneity in one of these treatment measures that we're using. So you can see around here, most of the plots, or most of the grid cells, have at least a plot that appears in 2012, but some grid cells kind of in the middle here appear much later. And that's something that we would kind of miss out on if we were using, much like larger units. And it's easy to imagine that this is only, right-hand side variation, but it's easy to imagine that for our left-hand side variable, we would also kind of miss out on heterogeneity like this if we used larger units. And then I also wanted to talk about kind of the remote sensing aspect of this a little bit. So there's a huge variety of satellite imagery products that are available. I have a list here that is definitely incomplete and kind of mentions the temporal availability and spatial resolution of some various satellite imagery products. I've worked with all of these, and all of them are free, at least to some extent. Planet and Google have sort of monthly quota plans that are free, and so I'm super happy to talk to anyone about using these sorts of data, which can be useful for kind of all sorts of things and making left and right hand side variables. Other remote sensing sources that are really common are weather data. So these typically either come directly from weather stations or are in the form of reanalysis data, which are a way of taking weather station data and combining them with a climate model to interpolate values over space. So typically that's a full grid of the world with values for different weather variables. Environmental quality sensors are great for looking at environmental outcomes when they're available. And then I've never used these kind of social network data, but there are a set of studies that have kind of recently come up that use these data to kind of make demographic characteristics at fine spatial resolutions. And so if anyone's interested, I thought that this kind of like fits with the theme of the talk on spatial methods, and I'm happy to point people to papers on that. We use MODIS for this project because it has pretty good spatial resolution and excellent temporal resolution. You get an image every day, and it's also available for a pretty long time. We also use some reanalysis weather data for additional kind of right-hand side stuff. So this is an image of the agricultural fires measure that we construct using those MODIS satellite images. So what this kind of shows is that there's pretty extreme variance in agricultural burning throughout Mexico. Some places have, almost a fire a day on average, and some have nothing. And burning is also pretty spatially correlated. So places that have high levels of burning tend to be located next to other places that have high levels of burning. One other thing I wanted to mention really quick is Google Earth Engine, which is an incredible and free tool for processing remote sensed data. So it's basically they have a lot of these data sources that I mentioned before, kind of already loaded up in the Google Cloud, and you can use JavaScript or Python to access them, process them, do various kind of manipulations to the data, and then download them in a way that would be definitely impossible on my personal computer. And it's really fast, and like I said, it's free. So I think it's a really awesome tool if you're interested in remote sensing.
Joel, just before you go on, there's a couple of questions in the chat about the fire measure that you construct. So Raphael's asking, in Modus, do they have nighttime lights, and how are you capturing the fires? Is that using nighttime lights? And then Rashid's asking, is that all or mostly residue burning, or are there other sources of burning, I guess?
Yeah,
bundled up here.
So they capture burning at day and nighttime. So there's a field in the Modus. So I guess maybe to take a step back really quick, there's a kind of well-known and well-designed algorithm for detecting fires in Modus. It's kind of been a long time interest of remote sensing people, and so there's a pretty, like I said, well-known and well-defined algorithm for finding fires in Modus images, and they've made basically another a product that does it implements all of the algorithmic steps to actually do this calculation. And one of the fields is whether or not the image was taken at day or night. And so I guess kind of unsurprisingly, it's easier to detect fires at night, but definitely most of the fires that we see in the data are from the day. And it's a lot harder to say for sure what exactly is going on with these fires. So the spatial resolution of Modus is 1 kilometer. So there's no way to know for sure kind of like what exactly it's associated with. What I've done here is I've limited it to fires that are on land that's classified as agricultural land in an INEHI data set. So basically it's a map that kind of says what land looks like agricultural land. I think they also use some sort of remote sensing to determine that. And then, so this is only showing fires that appear on that agricultural land. But yeah, there's no way to know for sure what how to actually attribute that to a particular activity. So now I'm going to get into how spatial data can help us in causal identification. So I kind of want to highlight some ways that once we start thinking about where units are located in space, we can kind of start to think about identification of things in new ways, or we can even start to identify things that maybe we couldn't have identified before. So some of the kind of issues that I want to highlight a little bit are dealing with time-varying unobservable confounders, looking at heterogeneous treatment effects, and dealing with or even identifying spillovers. You know, at least in observational research, there's no silver bullet with any research design. We have to be mindful of how we apply these designs, but I think that you know, thinking about space is very powerful and can help a lot with these sort of identification issues. So the first research design that I want to talk about is spatial first differences, which is a cross-sectional design that was developed by Hannah Druckenmiller and Solomon Shang, that looks almost exactly like a first difference estimator from time series analysis. And it essentially is, but instead of arranging units or observations in chronological order, we arrange observations in a spatial order. And so rather than taking differences over neighboring time periods, we take differences over neighboring units in space. And the reason this can work for causal inference is basically exactly the same reason that first differences can work for causal inference in time series, as long as any unobservable confounders are really highly correlated over space, or there's also kind of a more technical condition that can satisfy. Differencing will effectively eliminate them from the analysis. So to give an example of what a variable like that might look like, Tivrat Garg and co-authors have shown that agricultural wages affect agricultural burning because burning is a labor-saving technology. So when agricultural wages go up, burning tends to go up as well as people substitute towards it. But it's generally pretty hard to observe wages, especially for particular jobs, and especially at really high spatial resolutions and temporal resolutions. So this is kind of like a simulation that is based on that example. This left panel shows kind of the simulated agricultural wage that I made. So it's, it's high on the left and low on the right, but with, noise everywhere. The middle panel is a treatment, which maybe for this study we can think of as like Massagro extension provision. So it's high kind of in the middle and at the bottom, and is also generally higher on the left than on the right. So it's correlated with wage. And then the outcome, which is fires, is just a linear combination of wages and treatment. And we know that the true treatment effect is 1 in this, or -1, sorry, in this simulation. And so, we don't observe wages. If we run OLS with just the treatment effect is going to be biased because we've omitted an unobserved, or we've omitted a correlated variable. So we get attenuation bias, but spatial first differences completely eliminates this because wages are correlated in space, and we recover the true treatment effect. So spatial first differences, at least based on that, seems like a powerful tool. But like I said, there's kind of no silver bullet for research designs. Spatial first differences identification assumptions fail if there's even one unobserved confounder that isn't sufficiently correlated over space. Also, if the variance in the treatment is small relative to the variance in these unobserved confounders, then the estimate will be really, really noisy. And if there's measurement error in the treatment, then you get kind of really exacerbated attenuation bias, similar to the extreme attenuation bias you see in first differences in time series. But luckily, we can deal with some of these issues if we observe units more than once over time. So something that we're trying to work into the paper now is this thing that I'm calling difference in spatial differences, which is kind of a natural extension of spatial first differences to a panel setting. So basically the way it works is in every cross section, you run spatial first differences, and then you take differences between those spatial first differences over time. And so what this looks like in sort of a regression, you have to do the spatial differences is you just throw in a fixed effect for a unit or pair, depending on how you want to think of it. And what's nice about this design is that it's able to account for any time invariant confounders that aren't spatially correlated. So anything kind of idiosyncratic about location that helps determine the outcome but isn't spatially correlated over space is dealt with in this design. And also using only the variation in the treatment for a particular pair for identification can help increase kind of statistical precision. And so here's some results using this design with the data that I showed you earlier. This is for a kind of treatment dosage measure. So it's the amount of area that appears in the data that that Andrea was telling you about. This top row is those that adopt conservation agriculture. The bottom, or this orange one, is just any technology, and then these two are cumulative up to that year. And so, but results are broadly similar for no matter how we define this treatment intensity. What we see is sometimes significant but small results. Sorry, this is also effects for 1 hectare, so really small dosage, I guess. So what we see is pretty small effects for May, and sometimes statistically significant. Bigger effects for June and July, which are kind of at the end of the agricultural burning cycle, and then also big effects for November and December, which are at the beginning of the burning cycle. And then this is the same thing, but using a binary measure of treatment. So this is really like the first map I showed you. And again, what we see is smallish and statistically significant effects in May, bigger effects in June and July. The significance goes away in November and December, and there's also kind of an increase in January, although because this is percents, you can't see it in levels, but burning isn't super common in January, and so in a level effect, this isn't particularly big. This design has its own sort of set of weaknesses. So if there are any spillovers of treatment effects, like if receiving extension services in one place makes it likely that burning decreases in neighboring cells, we would expect a bias towards 0. Although it's not necessarily obvious that this would be the case if there's any sort of treatment kind of like amplification effects of spillovers. If you know about the negative weighting issue with two-way fixed effect estimators that Andrew Goodman-Bacon and kind of a other set of co-authors have recently pointed out, that issue is also present with this estimator, although hopefully some other aspects of the design help make sure that that isn't going on. And as I've written it out right now, we can't say anything about dynamic treatment effects. But there is a paper that came out just last week that actually deals with all of these issues. And I haven't fully worked it into the analysis yet, but I'm trying, and we'll kind of highlight some of the aspects of that design. So really quickly, if you aren't aware of kind of the issue with trying to estimate difference in differences with two-way fixed effects, basically if a treatment rolls out over time and we want to look at the treatment effect by comparing units that are and aren't treated before and after, using two-way fixed effects, so unit and time fixed effects, can be decomposed into all 2x2 different diffs. So that's just a group that doesn't change treatment status and a group that does in 2 time periods that appear in the data. And that even includes the ones where the control group is actually that is the group that doesn't change treatment status is actually a group that's already been treated, and the group that does change treatment status goes from untreated to treated. Those 2x2 different diffs in particular are assigned a negative weight when we aggregate up to make the two-way fixed effect estimator, And if there's treatment effect heterogeneity or treatment effects evolve over time, this can lead to really, really biased estimates of the average treatment effect on treated. So the kind of surprisingly simple maybe solution to this issue is that we should just estimate these 2x2 different diffs ourselves and only use the ones that are good in the sense that they use an untreated control group to make a measure of average treatment effect on treated. And that kind of logic has been followed in a number of papers that I guess started with that Andrew Goodman paper, but I think has been kind of most succinctly described in this Journal of Econometrics paper by Callaway and Santana, who give an estimator that not only does that, but also gives you a way to add covariates to the right-hand side in case parallel trends only holds conditional on some set of observables. They give you ways of doing statistical inference with this estimator, and they also give you they have R and Stata packages available to actually do this estimation for you. And so this paper by Kyle Butts just came out last week that gives a simple extension of this Callaway and Santana estimator that can account for and actually estimate spatial spillovers. So the kind of key idea of Kyle's paper is that it's better to actually try and estimate spillovers than to try and throw out units that might be contaminated by spillovers, because removing units removes statistical power or lower statistical power. So the only real assumption that we have to make to be able to actually model spillovers, at least to be able to identify a proper treatment effect, Kyle shows is that we just need to decide how far apart units have to be before there's no chance that one can spill over onto the other. And then what we do is just include an indicator for being close to a treatment unit by that definition, along with its interaction with treatment status. And this will totally remove the spillover bias. So for a 2x2 different diff, it looks like, first an ordinary 2x2 different diff with just post treat and post times treat variables, but then you include this close variable, which is the indicator for being close to a treated unit, and then close times treat. So the same variable, but interacted with being a treated unit. And the intuition for why this works is that basically you can decompose the treatment effect on the treated into what Kyle calls a direct treatment effect, which is kind of usually what researchers have in mind when we run difference in differences, plus the spillover onto treated units. So if we think of an intervention that has a positive treatment effect, if there are spillovers between treated units that sort of amplify treatment effects, that would tend to increase the treatment effect that we observe just by looking at differences in outcomes. So that gets added on to the direct treatment effect, and then minus the spillover onto controls. So if treatment can spill over from treated groups to control groups, that would tend to reduce the gap in outcomes that we see, which is why it gets subtracted from the treatment effects that we observe with the ordinary difference in difference estimator. And so basically, Kyle's approach directly estimates at least the average of these two things by just including them explicitly in the regression. And then once we start moving towards looking at multiple time periods, the same logic goes through, except instead of looking at changes, we're looking at differences in trends. So looking at identifying spillovers onto control works by basically looking for differences in trends between close and far control units, and then looking for spillovers onto treated units works in exactly the same way. We look for differences in trends for treated units that are close to other treated units and far away from other treated units. So I haven't been able to actually incorporate the spillover part yet, but this is output from Callaway and Santana's R package for June, and what you see is that there's kind of this notable slight decline in after the treatment is received, but none of the periods themselves are statistically significant. However, if you aggregate up and take the actual average treatment untreated, you get a minus 20% decline that's statistically significant at 5%, which is almost exactly the estimate that I showed you before with the difference in spatial differences. So maybe corroborates that finding a little bit and uses very different variation for identification. So the last thing that I want to talk about in research design is using weather for identification. So weather is really nice because it's definitely exogenous. We can't change the weather, and it exhibits a lot of variation at different timescales and is predictive of a lot of things. So it's generally useful for a lot of different studies. And so what we do is we try and use variation in wind to isolate the effects of, in wind direction, to isolate the effects of mass agro extension on infant mortality in urban localities through reduced residue burning nearby. So the intuition is basically wind transports smoke from fires over large distances, and as kind of shown earlier, treated cells exhibit less burning, or less fires at least, and so after they receive treatment. And so if we see more cells that are treated and upwind, that should imply that there's less pollution and fewer infant deaths in a locality. Some things we want to be careful of when we do this analysis, we want to be looking at the effect of having more treated cells upwind just by chance, not by the fact that you have a lot of treated cells nearby. And so that means we have to be a little bit careful in how we implement the design. And then also the effects of reduced pollution may not immediately materialize, and it's kind of unclear exactly how we should deal with that. So the first kind of way I have for trying to look at this is basically to control for the total number of treated cells nearby. So this specification does that by breaking up the total number of treated cells into those that are upwind. So the wind is blowing towards the locality. Downwind, the wind is blowing away from the locality, and neutral, which is neither of those. And if it's just an effect because there's a lot of treated places nearby, we would expect things to get loaded onto, beta neutral, because treated neutral is going to capture most of the variation in that. But if it's due to reduced fires, then we would expect the effect to get loaded onto beta up. And that's exactly what we see. So except for this one possible exception, we don't really see effects for downwind and neutral, but we see large negative effects for upwind. And they're largest at the point in the year where we saw the largest reductions in burning, but they're large throughout the year. The other solution is to basically account for the number of treated cells nearby by recentering. So this is a version of the Borusiak and Hole instrument, where basically what we do is we hold the set of cells that have been treated fixed, and we look at how many cells would be upwind if we saw, rather than this year's wind patterns, last year's wind patterns, next year's wind patterns, etc. We take the average of those and we subtract it from what we actually observe. So we only use the residual variation in that to predict how many cells should be upwind, and that should isolate the exogenous part of that. And so these effects are very different. These on the left-hand side should have, it should be moved out. It should be moved out 2 decimal places. So this is minus 50% and this is minus 100%. So we see some largish but statistically insignificant effects throughout most months, biggish effects in May and August, and then really big effects in July and massive effects in December. So importantly, both these sets of results can be right. We kind of by construction, this instrument is uncorrelated over time, so this probably captures more of an instantaneous effect, whereas the previous set of results I showed you, the number of treated cells upwind doesn't really do anything for it can be correlated over time, and so it maybe captures more of a cumulative effect. The last thing I want to touch on really quickly, I see that I've maybe gone a little bit over time, is standard errors. So some of these designs kind of naturally introduce spatial correlation and errors. So with spatial first differences, for example, you can see just by writing out the equation for 2 different observations, you end up with the same error term in 2 different observations. And if these individual error terms are IID, then the correlation should be negative between them. The correlation between the differenced error terms should be negative. So in principle, you only have to account for that. But in practice, it's, there's probably lots of things that might be uncorrelated with our treatment, but help determine the outcome and are spatially correlated, and we should try and think of what is the extent of that spatial correlation and try and deal with it some way. So definitely the most common way to deal with it is with Conley standard errors, where we basically say it's kind of like with the Kyle Butts paper. Up to some distance, errors can be correlated in cross sections, and we set that distance. And then errors can also be correlated within units over time. And Sol Shang also has Stata code to calculate these, and I'm working on some R code or publishing some R code that does it from fixest output. And then Driscoll-Cray standard errors are kind of an alternative that are definitely much less used. They're kind of interesting because they totally non-parametrically estimate the correlation between errors. So you don't have to do any of this stuff with what is the cutoff distance, but they rely on big T asymptotics, which usually we're not used to. And I'm not sure if there's a way of dealing with temporal autocorrelation with them. So really quick, the takeaways. At least for methods, when we start thinking about where units are in space, there may be some extra precautions we have to take when we start thinking about what is treatment, how do we measure outcomes, what are the units we're looking at. Remote sensing can kind of help deal with measurement of some of these things, and then designs that explicitly account for where units are in space can kind of address identification issues and concerns that maybe aren't necessarily available to designs that don't leverage that information. And when we do statistical inference on these things, we just have to be a little bit more careful as well. And then for the results that I've shown, it seems that moss agro extension helps lead to a reduction in the number of agricultural fires. And as a result, urban localities saw fewer infant deaths, presumably due to reduced air pollution. That's it. Thanks. And I think now we're going to take questions. Excellent.
Thanks so much, Joel. There was a few questions in the chat we can come back to, but so before getting to them, so anybody who wants to raise question or kind of discuss further, raise your hand, and then we'll can give you the floor. And so while people are raising their hands, let me check in with Prakashan with a question in the chat whether he wants to come back to that, and it has it's a different variation of treatment intensity, or in fact outcome intensity. Prakashan, if you're still here, you want to kind of come in? It means he's either not here or anymore, or doesn't want to come in. Kyle also had a question, though. I think you responded it, but Kyle, you want to expand a little bit, Kyle Emmerich?
Perhaps not much. I think that some of the graphs which showed the effects by month were sufficient there. I was just curious about the cropping calendar and when the fires were occurring, but when you showed the graphs with the effects by month, that for the most part answered that.
Yeah, there's definitely variation in when burning occurs, and yeah, so basically in the paper we try and break things out by month to kind of account for that and show how the effects are different at different points in kind of the burning cycle.
Yeah, but when you said it in words, you might want to make it very loud that like the levels are drastically different across those months. You said it. I think you might even maybe put the levels on a graph above or something like that, just to make it clear that those percentages are kind of hard to compare across months.
Yeah, got it.
Rashid?
Now it's working. Can you hear me? Okay.
Yep.
Thanks. Super interesting, and it's the data collection back regularly to the farmers through apps and extension is, I think, it's a fantastic effort in itself in terms of how to help the farmers, but also in what data it's collecting. And this is one example, very well executed, of what can be done with it, but it sounds like there's a huge potential of analysis that can be done out of it. And there should definitely be, I don't know, many partnerships and ways of thinking of what can be done with it. So that's great. Just some somewhat minor comments and different. One in slide 15, I'm not sure I would call it an attenuation bias. I would think of it as an omitted variable bias, which happens to go towards 0, but I don't think technically this is what I would call an attenuation bias, and if my colleagues would agree or not. Then I think if one thing that I find interesting, if they don't, it's presented almost as if not burning residues is okay. You keep this because that's what you're able to measure. I think it would be nice to think more of it, and then there is this focus on the effect on. There is a rationale for this as well. That is, can you reuse this for improving the soils? Even so, one thing is that measurable and observable at all? But even if it's not, I think it's really important to think of it as why is that an interesting outcome? As at least is it a measure of success in applying conservation agricultural practices? Is it okay? We should expect that this implies some improvement in soils. I think at least motivating the story also is important. Infant death could be caused by this kind of, and what's the magnitude of initially, is there any qualitative evidence of a lot of infant death happening because of air quality, and that wasn't obvious, but I think all this kind of thing, it's technically nice, but motivating the story around it, I think, is something that I could see that would help improve even more the work that's being done. And then on this this upwind treatment story, So at the end, you're using the average wind direction during the year to decide whether it's, or is it in, or can you use something as precise as you can in terms of wind during the day of the fire? Or in the sense that we need to think also whether, if I call it for me upwind, which is if it's before, in a way for its downwind treatment, should that affect me in some cases? If you say that on average I'm downwind, okay, but maybe on that day it was actually going that way, and hence I would expect that in maybe 20% of the cases it would also go the other direction. Or can you say something about, it's not, I've seen works with downstream in rivers, and there is no doubt because it goes 100% the same direction, but here it could go in one way or the other. So we kind of want to know, does it change regularly, or is it something quite consistent? I don't know about this. I think these are the main comments. So that we can think of, is that a real placebo, this upwind, or is it not?
Yeah. So I definitely agree on the attenuation bias thing. It's not attenuation bias because that's just from measurement error in the right-hand side variable. That is an unobserved and omitted variable bias that just goes to 0. Then, okay, so for the question of kind of like, what is can we say something about like, you know, the idea is that reducing burning is part of engaging in conservation agriculture, and like, is that effective and that sort of thing. There's a bit in the paper that uses some of the data that Andrea mentioned on profits. So we actually look at that and say, you know, it looks like on net, farmers are benefiting from this actual practice. So that uses the side-by-side plots so that there's kind of like this treatment and control that's at least within a farmer, so that we can kind of say, like, it looks like, you know, there's some sort of like, it looks like a causal effect of using this that is beneficial. And then for the infant deaths part, there's kind of like a big literature on the effects of air pollution, and infant deaths have kind of been found to be a variable, or, you know, a health response that is super responsive to air pollution. So that was kind of the reason for looking in particular at infant deaths. And then, yeah, sorry, I wasn't clear on the wind thing. We actually do it at the day level. So what we do is we say, kind of like for every cell, we can say like, what is the wind direction out of that cell, and does it point towards the locality for every single day? And then what we can do is kind of aggregate up to, so all the analysis is done at the month level, but we do that calculation every day, and then we kind of just aggregate up to the month.
Great. Joel, I wonder, I think Bram is still with us, and I hope Andrea's too. Kind of coming back to the previous question on, you know, which outcomes and also the, you know, in certain way, so if Bram or Andrea can comment on this. So the kind of one thing that would be interesting to know is whether residue burning was and the environmental benefits of it was part of, if you want, to the initial theory of change and the outcomes that you were anticipating to affect or not. And then I guess related to that in a certain way, so kind of, you know, the study is nice because it presents kind of a very rigorous approach to kind of, you know, measuring at least one outcome. But then I guess, you know, Rashid's point is kind of, well, but you know, the kind of, it's all about trade-offs and synergies. And so even if we can't measure them, we may kind of want to acknowledge those, or kind of at least want to see the bigger picture. I don't know, Andrea, whether you want to comment on that.
Yeah, maybe sure, comment if Bram wants to jump in as well. Yes, I mean, our main outcome or our main aim with the strategies are sustainable production. We have conservation agriculture at the center, as I said, and one of the main things we do with conservation agriculture is reduce burning, because burning is part of the traditional production system here in Mexico. So yes, it is embedded in what we at the beginning knew we had to do with those ecosystems, let's say. But yes, of course, we were not expecting or anticipating these sort of analysis out of the data set that we had.
Thanks, Andrea. Just to confirm, I think Andrea puts it very well. If we are very clear in the original theory of change, non-burning or leaving residue in the field was part of making a sustainable production system, which obviously gives environmental benefits. But I think we probably, if we are clear, looked at it more at the field. I mean, what residue can do for field production, what it can do for biodiversity in the soil, what it can do for carbon and nitrogen cycling, etc. The fact that it has an impact on some of the parameters now measured in this study was not part of the original theory of change, but rather kind of an additional, well, call it an additional benefit that we were aware of, but probably not really intended to measure, as also the donors supporting this project themselves are now surprised and actually using this to unlock resources with other secretaries. So basically the Ministry of Ag was the driver of these interventions, and they're now talking to the ministry together with the Ministry of the Environment, but they're now starting to talk to the Ministry of Health, saying, okay, we should invest in this together because it goes beyond. But that was not, I mean, if you're clear, it's more a peripheral. So I actually think we can take this a step further by, what I find interesting about the study is that actually by looking and seeing what we can do, you push probably the envelope of your perceived theory of change. And I think actually we should use some of those studies a bit more to say we can probably be a bit more ambitious, or we probably need to break out of our framework of thinking, and we can now deliberately probably look at other interventions from the same outcome that we want to provoke. I don't know if I'm making myself clear, but let's look at health and say, okay, are there other things we actually can optimize that we are today not optimizing because we were never looking at that particular outcome to provoke, while we actually could, while we still keep all the other objectives going. I hope it makes sense what I was a bit thinking and talking at the same time, so I hope this.
No, it made perfect sense, and I think indeed, I mean, it's a great example, both in terms of the policy, like how the evidence kind of crowds in additional policy interest, but also how it then, you know, expands the learning agenda, kind of going forward to think about that. I see another question in the chat from Marie-Charlotte. Marie-Charlotte, you just want to ask it, Orly?
Yes, yeah, yes. No, well, I was interesting because I have more experience in India where residue burning or another. I mean, the reason for residue burning is quite different from what you are presenting here. So that's from where I'm coming from. But you mentioned the residue burning as a labor-saving technology. So since there is this discussion and the different outcomes that we can look at, I was also wondering if you know anything really on the effect it would also have on the labor and potentially on the wages. That's what I had in mind.
Yeah, I don't know of any. So there are two papers that I know of that go in the other causal direction. So the Tivrat Garg and co-authors paper that I mentioned in the slides basically looks at this rural road building program in India, which a kind of really big comprehensive study showed didn't affect many outcomes, but did definitely affect the sector that people were employed in. So a lot of people moved out of agriculture once these rural roads came in. And so they use that as that variation to say something about what happens to burning, because the idea is that these people are people in these villages that, or rural towns that get these roads. Once they move out of agriculture, it changes agricultural wages, which they tend to go up. And then what you see is that the number of fires near the places that got these roads also goes up in response to that. And then also in India, there's a paper by Patrick Bearer, who looks at the rural work guarantee, and he kind of finds similar results that once that was rolled out, you know, that also raised kind of like the agricultural wage, at least in certain parts of the year, by changing agricultural workers' outside option, and that also led to increased residue burning. But I don't know of any papers that go from what happens to residue burning to what happens to wages. It would be interesting, I think, to look at that.
I think Andrea wants to comment. Just go ahead, Andrea, take the floor.
Yeah, thank you. Just to comment that based on our experience, when we introduce the whole package of agriculture, conservation agriculture, to these particular systems, what we see is conservation agriculture takes time, and it has an increase in costs from year 1 to year 3, and then you start seeing the actual benefits. For instance, if you have a dry year, your yield is going to maintain. I mean, it increases resilience very notably. So even though they have to stop burning, and it means higher labor, but in year 1, 2, and 3, when it comes to a dry year, or they can actually see the benefits, then it balances it by itself. Yeah.
And just to complement, I think here the importance, and to complicate the story a bit more, is that we accompany usually these elements with smart mechanization. So you add another element, I know, but it's exactly because of the labor sitting as a decision-making element in the decision space of the farmer, burn or not burn. So indeed, the labor parameter is very important. So usually also those programs, and it is not different with Masagro, go accompanied by smart mechanization, which then actually plays with that parameter of the labor cost, and resolves 2 elements: the labor, plus there is a physical element, right? You need to get the seed in the ground. So and residue can be annoying if you want to get a seed in the ground. It can it's a very simple practical thing. If you have tried to plant in the field with a lot of residue, especially in India, where the previous speaker was referring to, I mean, rice residue is that's the top of annoying residue, right? So there's a practical element also that you need to overcome, which is also tied to that smart mechanization to overcome that practical issue as well as the labor issue.
Yeah, makes sense. Rashid, go ahead.
Thank you. No, super interesting, all these things we're hearing. How much, so like this last story sounds like so there are not that many successful stories about conservation agriculture. It's always not so clear what would be the effects and how much time it takes to see the benefits. So one of the elements of the story that I hear seems to be a kind of a big push story in terms of if you just adopt a few of these, it's not working that great, but you really have to compensate on one side the additional labor that it takes by also adopting the mechanization, and you don't need to give up on the fertilizer. It seems like it's part of the story. How much of a even more descriptive analysis was done also to draw some bigger picture lessons? I guess part of the recommendations that are done seems to be based on this cluster level analysis that you do. And do you have just descriptive stories of kind of before and after adopting it and the trends of how things seems to be changing?
Yeah, sure. I mean, this is one study in a whole set, and actually what I like about this study is that we were doing stuff for 10 years and somebody external came in and said, hey guys, you didn't see there's an angle here that we can be looking at, and those are the ones I personally like the most, because they push the envelope and they bring in a new way of thinking. So there are basically we have studies, let's say that We have CIMMYT-driven studies that look really at project compliance, all the way down to externally paid, externally implemented people just saying, I want you to use your field laboratory. So there's a whole environment of studies. What's probably not there is a kind of a coherent, call it meta study integration that brings it all together. So I think there, Rashid, you put your finger on a pain point that yes, we don't have kind of a coherent integration of all those different studies, observations, descriptions that have been done as well internally as by external partners. How to resolve that, I don't know, but it's a good point for us to take home.
And yeah, and related to this, I see this, how this whole production function looks like. Do you need to use all of it together, or some pieces work well? How far can you go in terms of really telling? It's a multi-dimensional production function, so it's very complicated, but how much can be said based on the very rich data that you have seems to be a very interesting way to push it.
Yeah, absolutely. And to make it a bit more complicated is that, I mean, it's going to depend also on the agroecology where you are and the production system where you are, as those drivers are very different in each of those systems. Now, here, Joel is mainly focusing on a particular area with a particular production system. We have the same efforts in different other agroecologies with smaller farmers, with connected to market, not connected to market. I mean, so there's a whole, so that makes it even probably more complicated, but more interesting, because actually you could confront, right? Is there a different decision-making pattern, and are there different important parameters for those decisions if a farmer is market connected or not? Something like that, just throwing something out there.
Excellent. Well, thanks everybody for these thoughts and inputs. You know, this is clearly fascinating. We can keep on talking for a couple of hours. But I think this last discussion also points kind of just, if you think indeed to earlier puzzles in this literature of low adoption of conservation agriculture, and in a certain way, Joel, you jumped that part. Kind of, here there is adoption, and then we can look at the impacts. And which are super interesting and unanticipated, as we heard, which makes it arguably even more interesting. But there is that other part of the picture, clearly. And somebody should write the book, Bram. I'm not sure that's you or somebody else, but
I definitely propose a ghostwriter, but yes.
Excellent. Well, this was great. Thanks so much. I think I learned a lot. I hope other people learned a lot. It's the other part. What is interesting about this study that is worth looking in, I think, for other CGIAR innovations, is in a certain way the data infrastructure that made this possible. And so and a lot of credit there, I think, also in having that. Not just having it, but having it organized in a way that can be used, and thinking through the incentives for people to collect that data, etc. And I think there's a lot of learning that, we're out of time because that was going to be my next question. But certainly, I guess, encourage the team also to share those lessons more broadly, because I think there's a lot of that other teams can learn from this. I think. Excellent. So with that, let me just thank Joel and Andrea for being here, for super interesting food for thought and presentations. Joel also for getting up very, very early. And Bram, thanks for your inputs, and everybody else who was there, who participated with questions and comments. Thank you very much, and we will see you in 1 month. Take care. Bye.
Bye-bye. Take care. Ciao.